Hello, this video is covering the homework Unit 6 Module 2A and B. We're going to start with the strong acid and base calculations. They are the most straightforward to cover, so we will start there. Right, so the first thing is which acids are strong, and there are three of them. Now there are more in the world, but in general chemistry you are only responsible for knowing these three. It's HCl, hydrochloric, HNO3, nitric, and H2SO4, sulfuric acid. So the equation here to find so we're given that the pH is 1.9. So these are the two equations that relate hydronium ion concentration to pH. So either you're given the hydronium ion concentration and you're asked to calculate pH, or you're given pH like in this problem and you're asked to calculate hydronium ion. There's only two possible calculations. Right, and so what does strong mean? Strong means that the concentration of hydronium is the same as the concentration of the strong acid. It completely reacts. There is a 1-to-1 conversion. So HCl in water is all hydronium, all H3O+. Okay, so when we solve for the concentration by taking 10 to the minus 1.9, 10 to the minus pH. When we do that, we get 1.3 times 10 to the minus 2 molar, and that is the concentration of hydronium, and it's the concentration of the strong acid. They're identical. For the base, you are responsible for recognizing strong bases or any metal hydroxides. So this is going to be different than a carbon that looks like it's attached to a hydroxide. That is, even though that's considered a hydroxyl group, the carbon, oxygen, H, the COH is not a strong base. So that's really something to be careful with. But if it's a metal, like potassium and sodium, any type of element that's on the left-hand side, hydroxide, then it will be a strong base. So this, for most of our work, this is potassium hydroxide, sodium hydroxide, lithium hydroxide. So any metal hydroxide is going to be a strong base. And just like we said above, that means that the concentration is the same as hydroxide ion concentration. So when we say KOH so this is identical, right? So potassium hydroxide, if you have 0.008 molar potassium hydroxide, then that's the same as hydroxide ion. So complete reaction with water. That's what we mean by strong. So 8 times 10 to the minus 3 molar. So once we have hydroxide ion, most students, I know there's a couple ways to go about this, but most students I work with do this step. So the first thing you do is you take the minus log of your hydroxide ion concentration, and that gives you POH. So POH is 2.1, and now we can solve for pH by 14 minus POH, and 14 minus POH here is going to be 11.9. So 11.9 is going to be the pH. It's basic. It is above 7. And that's what we would expect for a hydroxide, enriched solution of hydroxide ion. Okay, but most of our work isn't strong acid and strong bases. It is weak acids and weak bases. So we're going to go through some calculations of weak acids and weak bases. Remember, these are all reactant favored. Okay, so weak, meaning K is much less than 1, meaning reactant favored, right? So we're almost all of the reactant is unreacted, and that's very important. So Ka first of all, produces hydronium, right? That's one of the keys to recognizing any equilibria is by looking at the products and saying, do I see H3O plus or do I see hydroxide ion? So pKa is minus log of Ka. Ka is minus, if you want to, so these are the two equations that can be used if you're given one value and you're asked for another. This happens a lot. So, and what is Ka? Ka, just like last exam, are the concentration of the products over the concentration of the reactants. And here we observe there's only one reactant that goes into K because pure liquids do not go into the equilibrium constant. Right, so Ka, so numerically, so that's the expression of the equilibrium constant. But numerically, we can calculate this ratio by taking 10 to the minus pKa. And if we do that, 10 to the minus 2.87 is 1.3 times 10 to the minus 3. Much, much less than 1 reactant favored. So this is a typical calculation you're asked to do. You're given a reaction, you're given a pKa, and you're asked to find out what is the equilibrium constant for that reaction. Now, how is KB involved? Well, imagine you had a problem. So let's take a look. So Kb is also weak. So a weak acid produces a weak base conjugate. And we can put this weak base conjugate in water also and do calculations. So let's take a look at that. So again, these are always going to be reactant favored. So Kb here produces, the products contain hydroxide ion, right? So clearly the reaction above is not Kb because it's producing hydronium, but we can look at what would be the Kb reaction for this, looking at its conjugate base. So Kb is the minus log of Kb, and Kb is 10. You can calculate Kb as 10 to the minus pKb. And if we do that, to get Kb, we need to, remember, pKb is equal to 14 minus pKa. This has a very similar relationship to the pH and pOH, which we can sort of put here, which is pH plus pOH equals 14, pKa plus pKb equals 14, right? So those are the two relationships with P that are important to keep in mind. And if we look at that, we get 10 to the minus, we could incorporate the negative sign, and if we do that, we get 2.87 minus 14, or 10 to the minus 11.13, or 7.4 times 10 to the minus 12. So Kb for this system, right, so this is an acid who makes a conjugate base, right? This is the conjugate base right here. And if you put that conjugate base in water, right, this would be its equilibrium constant. So which reaction are we talking about? It is the conjugate base. We know it's a base because it has a negative charge. So we put this negative charge in water. That will remake the acid form plus hydroxide ion. So that's the reaction that pKb and Kb are referring to. It is not the reaction given to us. It's the reaction of the product that's made, this product that's made in water to produce hydroxide ions. And it's really important to be able to navigate that aspect of these problems. And again, it's always reactant favored. Okay, so why did we do that? Well, we did that because now we're given both pKa and pKb. Remember, there's sum here. The sum of these two is 14. And we're given the pH is equal to 2 times 10 to the minus 14 molar of this molecule, ketoprofen. And now we want to know what is the pH. So we did several of these calculations in class, but now we're going to sort of work out this in graphic detail. So remember, keep in mind acids for our class. Weak acids look like this. You either have the COOH, right? That's what we're talking about. This is COOH. Or we have the NH plus, right? Those are the two that react in water to undergo Ka and produce hydronium ions. Bases, right, are the negatively charged, the conjugate base of a carboxylic acid, or the neutral nitrogen with a lone pair. So the question is, what is the pH, knowing that C0 is 10 to the minus 4 molar and that pKa is 4.4. Now we know we're undergoing pKa because acids undergo pKa, bases undergo pKb or Ka or Kb, right? And they produce H3O plus and produce OH minus, right? So that's what we want to keep in mind. Every time you look at a molecule, you want to be thinking about it this way. So these are one of the equations we had on our in class. So hydronium is equal to C0 times the square root of C0 times Ka, which we can modify C0 10 to the minus pKa, right? So that's one of the convenient formulas. And we're given C0, we're given pKa. We can solve for hydronium. Put in the numbers. And we get 8.9 times 10 to the minus 5 molar. So the pH is equal to minus log of 8.9 times 10 to the minus 5 molar, or 4.0. So the pH of a solution, it changes, right? It changes. This increases this very weak acid with a very low concentration. When you put this in water, it changes the pH 3 orders of magnitude. It goes from 7, which was pure water, down to 4. Now, what we could do is students always ask, well, why did they give us pKb, and what would happen if this was a pKb problem? So if it were a pKb problem, whoops, okay, so let me sort of erase this part here, because I'm going to sort of write in this part, looks like. Okay. So what is the pKb? So if we had 2 times 10 to the minus 4, but instead of the molecule given, right, instead of ketoprofen, we were given the base form like that, and that's usually given in the form it's usually given in the form has a negative charge, and it's oftentimes paired with the sodium ion, right? Because you can't have a negative charge without a positive charge. But so this guy, this negative charge, is what we would see here. So if the problem had been that we had 2 times 10 to the minus 4 molar of the negatively charged ketoprofen, then what will we do? And what we would do is we would first calculate hydroxide ion concentration, because we'd be working under Kb, as C0 times 10 to the minus pKb, right? So that's the equation, that's the difference of whether you're working with Ka or Kb, that you have to solve for hydroxide ion if you're working with a base. If you do that, you get 2 times 10 to the minus 7 molar and of hydroxide ion, which you can convert to POH, and if we do that, we get 6.6. Now, are we done? The answer is no, because we were asked for pH, so we're going to do one extra step. Just take 14 minus 6.6, and we get 7.4, which is greater than 7. So it is a basic solution, which is what we would expect by putting a base in water. Okay, So here's the problem. The problem is, I think this is morphine, maybe, and we're given. So we recognize that this is Kb, and we're given a pH. We want to know what is the pH of the concentration. So what we do is, the equilibrium that this would undergo is Kb. Why? Because it's a neutral nitrogen in water. It's going to produce its conjugate acid, positively charged nitrogen with 4 bonds, and hydroxide ion. So let's look at the roles of all of these molecules. So the base, neutral nitrogen, is going to convert into an acid in the products through its conjugate. Water, which is acting as an acid, it's donating a proton here. Its conjugate is a base, and that's the hydroxide ion form, Kb. So if you want to know if you're undergoing Kb, if the reaction is Kb, then you just have to look at the products hydroxide ion. All right, so we can solve for hydroxide ion here, C0 times Kb, or C0 times 10 to the minus pKb. We do that, we can readily calculate the concentration of hydroxide ion as 5 times 10 to the minus 4. We can then use that value by taking the minus log of the concentration of hydroxide to get pOH of 3.3. And the pH is 14 minus this, and you get 10.7. And what you have to be careful about is in a lot of these problems, 3.3 is going to be one of the answers for the pH, right? And it's not the pH, it's the pOH. So you have to be careful with that. This is a basic solution. Basic means it's a basic solution. We're putting a base in water. It has to be greater than 7 if basic, right? So that's important. And so when we're looking at the pH scale, acids are between 0 and 7. Bases are between 7 and 14. And the products, right? If you undergo Ka, you produce an acidic solution. If you undergo Kb, you produce a basic solution. Whoops. And in this case, we put 10.7, so we're definitely producing a basic solution. Okay, so this is the second part of Unit 6, Module 2a and b, and it has to do with shifting. So let's talk a little bit about, we're given Ka, reaction, and what we want to do is what happens if water is added to the system, right? So if water is added to the system, what do we expect to change? Now, many students come into office hours to talk about this problem, and one of the major reasons is because there's 3 parts of this analysis, which makes it fairly complicated if you put all 3. But if you take it step by step, then you can systematically isolate the correct answer by first looking at what happens with pH, what happens with hydronium ion, and then what happens with the moles of hydronium. So we're going to take a look at that step by step. All right, so the first step is what is the role of whatever you're adding, right? So if you're adding HF, what's its role? If you're adding hydronium, what's its role? Now in this case, we're adding water, and if we look at the role of water in this problem in Ka, water acts as a base. Right, it's accepting a proton from the weak acid HF. So right there, that tells you something about what happens to the pH. If you add a base to any solution, the pH must go up. So that's the first analysis, and we see that only A and D have that correct assignment. B and C are saying, oh, we're adding water, but we have acidic solution, and it's getting more acidic if we add water. And B and C are wrong for that reason. So now we're deciding between A and D, and what's the difference? The difference between A and D is A says hydronium ion concentration will go down, and D says hydronium concentration will go up. So let's take a look at so what we're going to do is go through the full kinetic analysis here to make sure, we always ask this on tests, so you want to make sure that you can build this argument. So let's look at step one. So the first step in the kinetic analysis is the recognition that at equilibrium, rate forward equals rate reverse, right? So that's number one. So your system starts at equilibrium. Step two is you stress the equilibrium by changing one or more concentrations immediately. So let's take a look. If we add water, we dilute the system, so the concentration of HF goes down, the concentration of F minus goes down, and the concentration of H3O plus goes down. So now we see right away in 2 that the answer has to be A, because the hydronium ion concentration must go down if you're diluting your acidic solution, right? So we kind of have that answer already, but let's go through all the steps. So now, based on this, we see the rate forward is moving faster than the rate reverse, because the rate reverse involves 2 concentrations going down, but the rate forward only involves 1 concentration of going down. So the rate reverse is going down faster than the rate forward. So because of that, the third step here is a shift. We're going to shift material in the equilibrium to reestablish equilibrium. And what we do is we always shift to the side that's moving slower. That's what it comes down to. So we have to shift. So the forward is moving faster than the reverse, so we have to shift to the reverse. We have to shift to products. If we shift to products, right, that means that the amount of moles of H3O plus must go up. The moles of H3O plus has to go up because H3O plus is a product. So if you shift to products, you're making more H3O plus. If that's the case, then that's the origin of the answer, right? The answer A is first, the concentration of H3O plus will go down because you diluted the problem. 2, the net amount of H3O plus will go up because you're shifting to make more products. So when we kind of look at this answer, dilution, so first, by adding a base, we know the pH will go up. We know the concentration of H3O plus will go down because the dilution. And finally, the shift, the net amount of H3O plus will go up, and that comes from our shift analysis. So it's a challenging argument to make. You have to kind of do it step by step, but these are all the steps necessary to pick A. So D would be wrong. So B, C, and D are wrong. Okay, so here we're given a strong acid and metal at equilibrium. So we're putting sodium metal and HCl gas. We're making sodium chloride salt and hydrogen gas. We're just going to take a look at all the different ways this system can change using the kinetic argument. So first, as you know, when you build your rate laws, rate forward is K times HCl squared. K reverse is H2. Now remember, no solids can be in the rate law, so we're only looking at that aspect of the problem. So the first analysis, what happens if we add more sodium metal? No effect. So the reaction takes place just as fast because sodium metal is not in the rate law. If we add NaCl as a product, no effect because, again, it's not in the rate law. All right, let's add HCl. All right, so if we add HCl, the rate forward goes up, right? Because HCl is a reactant. It's Kf times HCl squared. So if you increase that concentration, rate forward goes up. Now rate reverse is going slower. So whatever's moving slower, shift to that. So the shift must be to products. You make more H2. If we add H2, which is a product, that means the rate reverse goes up. If the rate reverse goes up, it's now moving faster than rate forward. Since rate forward is moving slower, we shift to reactants because that's the side that's moving slowest. What happens if we lower the volume? So this is a question that's often asked, especially on homework. So we take a look. Well, how would volume affect this? Well, they're gases. So that means if they're gases and you lower the volume, your moles per volume has just increased. So if your moles per volume has gone up, the concentration of the gas has gone up. And so HCl goes up, but it goes up twice because it's squared. So that's moving faster than the reverse reaction, although H2 did go up also, but since it's only to the first power, it didn't go up the same amount. Rate reverse is moving slower, so we shift to products. So that's how we would look at all the different aspects of this problem. Adding reactants that are not in the rate law, no effect. Adding reactants or products that are not in the rate law, no effect. Adding reactants, you shift to products. Adding products, you shift to reactants. And if you change the volume, because these are gases, you have to do the analysis based on what is affected most, and whatever is affected most is going to determine the shift. Okay, so let's take a look at another problem. Here we have KB. I'm just going to change this problem to just evaporation because we already did water addition. So let's look at the type of problem in which water is evaporated or removed from the system. So first we look at the role of water here. So the role of water is as an acid, right? So under KB, we know we have KB because there's a hydroxide ion. And so in KB, water acts as an acid. If we're adding an acid, no, actually we're not adding an acid here, we're removing an acid. So if we're removing the acid under evaporation, this has to become more basic. So if you remove acid, it becomes more basic. If you add an acid, it becomes more acidic. All right, so that gives us a starting point that we know that this is going to be more basic. pH must go up. Now the other aspect is all concentrations will go up because we're evaporating water. So they all kind of go up the same. So let's see how that affects our rate laws. So we write the initial equilibrium condition, rate forward equals rate reverse, K times the reactants equals K reverse times the products. And so you see one thing right away, which is the products are always affected more by the addition or removal of water. And that's because there are two products versus one reactant. So the stress is that the rate forward has now gone up, but the rate reverse has also gone up, but it's gone up by a factor of 2 because there are two different reactants whose concentrations have immediately increased because of the evaporation. Since rate forward is moving slower, the shift has to be to reactants. You have to make more reactants to reestablish equilibrium because the rate forward is moving slower. So you always shift to the slower side. The reactants are the slower side. So what we would expect is hydroxide ion concentration will go up through evaporation, but the moles of hydroxide ion will go down, and they go down because of the shift. The shift must transfer products over to the reactants, and by doing so, that means it's going to consume some of the products. OH minus is a product, so it's got to shift to shift over to reactants. It must consume hydroxide ion, and so the amount of moles of hydroxide goes down. Okay, so first B and C are wrong because if you evaporate a basic solution, you will not make it more acidic. So B and C are wrong. The only choices are A and D. We expect this to become more basic. We expect we're removing an acid or the role of the acid water, so pH will go up. And now with evaporation, we expect that pH concentration will go right, the OH minus concentration. So I know this is, this is dilution, but it's not dilution, it's evaporation. So under evaporation, the concentration of hydroxide ion will go up, but because there's a shift to reactants consuming OH minus the product, that's why the moles, the net amount, the moles of hydroxide ion will go down. Right, so that is Unit 6, Module 2AB review homework. Keep in mind that Exam 3A has both of these homework sets. There are videos covering worked out problems, at least half of them are worked out here in this video and the Unit 6 Module 1 video. If you're unable to come to office hours, I really encourage you to watch these.